The question that we are going to answer today is, what is the difference between feasible and optimal solutions? This question we might feel like answering once in a while whenever we are dealing with any kind of optimization. So let me ask you a very simple question. Suppose you're packing a bag for a flight and the airline says that your bag must weigh under 20 kilograms and you pack 18 kilograms. Does that mean that you packed optimally? Not necessarily. You satisfied the rule that you are under 20 kilograms, but maybe you left behind something important. Maybe there was a better combination of items. Being allowed to board the flight doesn't mean that your packing was the best possible packing. So, this gap between it's allowed and it's the best is one of the most important distinctions in all of optimization. And today we are going to make it completely precise. So, before we define and talk further about the feasibility and optimality, we need one foundational idea about the solution space, also called as the search space. Every optimization problem has a set of decision variables, the things that you get to choose. In a scheduling problem, these might be which server handles which task, in what order, at what time, etc. The solution space is the set of all possible combinations. So the solution space is the set of all possible combinations of those decision variables. Every single point in that space is a candidate solution, a complete assignment of values to all the variables. So one of the critical insight that we might have in this case is that not all the candidate solutions are equal. So from the set of all the possible combinations, we have some candidate solutions, and not all the candidate solutions are equal. In fact, they differ along two completely separate axes. The first axis is legality. Does this solution satisfy all the rules? Does it respect the weight limit, the deadline, the power budget, etc.? This question is of feasibility. The second axis is quality. Among all the legal solutions, which one is the best? Which one minimizes the cost, maximizes the performance, achieves the goal most fully? This is the question of optimality. So these two axes are independent. A solution can be feasible but terrible. A solution can be optimal looking but illegal. Understanding this independence is the core. So if we talk about feasibility, the first case, formally, a solution X is called feasible if it satisfies all the constraints of the problem. That means every inequality constraint Gx less than equal to 0 holds, and every equality constraint Hx is equal to 0 holds exactly. If one of the constraint is violated, the solution is infeasible. If one of the constraint is violated, it becomes infeasible. It doesn't matter how good the objective value looks, it's outside the rules, and in a strict optimization sense, it doesn't count as a valid answer. So, example, if we take about the task scheduling, we have four tasks, and two servers. The constraints can be each task must be assigned to exactly one server, that is equality. Total CPU load on each server must not exceed 100%, that is about inequality. Task 3 must complete before task 4 starts, that is the ordering constraint. A candidate solution that assigns task 3 and task 4 to the same server out of order violates the ordering constraint. Okay, so this is another constraint we have about ordering constraint. So if the constraints are not fulfilled, this candidate solution cannot be submitted as a valid schedule. There will be fault down the line. Now here's something important that many beginners often miss, that is feasibility says nothing about the quality. Imagine a scheduling problem where the best possible make span, that is the time to finish all the tasks, is 10 seconds. A solution with a make span of 97 seconds that satisfies every constraint is perfectly feasible, but it is illegal and it is very bad. So instead of having 10 seconds, something is suppose finishing in 97 seconds. However, um, it is a solution and it satisfies every constraint, but it's feasible, right? But it's very bad. So feasibility is the floor. Feasibility is the floor. That is the minimum requirement. It gets your solution to the room. It doesn't tell you where in the room you should stand. One more concept worth mentioning here is about the feasible region. This is the subset of the entire solution space that contains only feasible solutions. So we are having certain candidate solutions out of which we are having certain feasible solutions. So this is the legal territory. Everything outside is just forbidden. So in a well-structured mathematical problem, the feasible region has a clear geometric shape. In real engineering problems like IoT, edge, cloud scheduling, the feasible region is irregular, sometimes disconnected, and very hard to characterize analytically. So, this is exactly why we need intelligent search methods. So, now let us define optimality, and this is where it gets more nuanced. So, a solution, if you talk about optimality, there is a solution X star. It is called globally optimal if it is feasible and no other feasible solutions has a better objective value. So it's the best of all the legal options. However, here is what the things need to be taken care very carefully because there is a concept that is known as the local optimality. A solution X is locally optimal if no solution in its immediate neighborhood, solutions reachable by a small change, has a better objective value. It looks like the best point from where you are standing, but there might be a much better solution far away that you can't see. So, we saw certain examples last time, some graphical examples where we are having some uh, valleys and crevices, and we found that the global optimum and local optimum can create certain serious issues in case of optimization. So, global optimum, the single best solution across the entire feasible region. Suppose this is the feasible region. It is unique and there is no better answer. Local optima, that is the best in the neighborhood. So, no small perturbation improves it. A problem can have hundreds of local optima. Most metaheuristics will find one. The art is finding the global one. So, we have to find the global optima. But suppose using certain metaheuristics, we have found one local optima, but then we have to explore to find out more. So, near optimal solutions, Near optimal solutions, these are feasible within a small acceptable margin of global optimum. So for most practical engineering problems, this is actually good. Not the exact optimum, but something close enough to matter. So an important thing about this is that optimality is always defined relative to the feasible region. Optimality. So a solution would be optimal if you could ignore the constraints, and a solution that's optimal within the feasible region might look mediocre compared to the unconstrained optimum. So this is where we say that searching for the constraint optimum, that is the best answer among all the legal answers. So I hope you're clear with these 2 points about the optimality and feasibility.